Welcome to Science Spectrum with Don. This is Math 188, the fundamentals of mathematics, and I'll start off with the first part of the third lecture in trigonometry. Alright, trigonometry finds, this aspect of mathematics finds application in navigation, surveying, okay, and even in animation and the likes. Now, the word trigonometry was coined from the Greek word trigonia, metron. Okay, this is the Greek word, okay, from which trigonometry was coined from. So, tri is 3, gonia means angle, then metron means a measure. So trigonometry, you could say it's 3-angle measure, or you could say it's a measure of 3 angles. And of course, the geometric shape, okay, that has 3 angles and 3 sides is exactly a triangle. So you have something like so. And then, by the way, when 2 line segments meet, okay, when 2 line segments meet, for example, I have a line segment like so, and I have another line segment that meets at these common endpoints, okay, with the first line segment. Clearly, an angle is formed here, right? So this angle formed could be measured in terms of a degree, or you could see it as, okay, a measure of this arc, and that's in radian, okay, if we assume that, okay, this is, okay, I form a perfect circle now, like so, and this turns out to be the radius, okay, of the circle. So this is a measure of the angle in radians, rad, okay, and this angle theta, okay, could also be in degree, right? So this is simply, okay, how angles are formed. So for a triangle, okay, a measure of 3 angles, you have something like so. So this is just a generic representation of, okay, a triangle. And now, a mathematician by the name Hipparchus, he was Greek, Hipparchus, in 140 BC, was the first to establish the relation between the sides and the angles of a triangle. Alright, so let's move on now. So having talked about the fact that an angle, okay, is a triangle is a 3-sided polygon, okay, a 3-sided polygon. So that's a triangle. That's what this branch of mathematics, trigonometry, is all about. All right, so let's move on. Now we'll talk about briefly. Let me talk about briefly about the types of triangle. Okay. The types of triangles, So the first one is a triangle like so, whose sides, right, and whose angles are equal. Right, so you are free to imagine this is side A, this is side A, this is side A. All the sides are equal. And if this angle is angle, okay, let's say, and this is angle theta, this is angle theta, this is also, okay, angle theta. All the angles are equal. This kind of triangle, we call this an equilateral triangle. So it's a triangle whose 3 sides and 3 angles are equal, right? So if that's the case, it simply implies that each of these angles is exactly 60 degrees. Alright, now the perimeter is the distance around a triangle. So when you go from here, right, to here, like so, right, you go like so, you walk across the lines, right, and you go like so. So when you go around the triangle, that's really the perimeter. And the perimeter is computed by, okay, adding or summing the sides of the triangle. Now the area the area of an equilateral triangle. Let me talk about the area. The area of an equilateral triangle. Okay. So in this case, the perimeter of the triangle. Okay, triangle has this shape. Is a plus a, right? And that gives okay, 3 times of the side. 3 times, okay, its side. And of course, this would be, okay, in units, in any units you prefer. Okay, this could have been in centimeter, meter, millimeter, okay, and what have you. Alright, so let's talk about the area now. The area of, okay, an equilateral triangle is given by this formula. The square root of 3, which is the same as 1.732, divided by 4 times the side, the value of the side, which is the same, raised to power 2, and this will be in square units. So I give a working example just to concretize this. Let's take, for instance, that if the side, this is 3 centimeter, this is 3 centimeter, this is 3 centimeter, and for now, okay, I'm just imagining that the angles, which I know are equal, okay, are not given, but the 3 sides are given. So this is for the area of an equilateral triangle with the 3 sides given. So the area, okay, becomes the square root of 3 is 1.732 divided by 4. Then the side is 3, right, centimeter, and it's raised to power 2. So this becomes 1.732 divided by 4 times, now 3 raised to power 2 is 9, and centimeter raised to power 2 is, okay, squared centimeter. We need to write this here, squared centimeter. So division comes first before multiplication. So I will divide out 1.732. So I will divide 1.732 divided by 4. So the answer turns out to be 0.433, and of course I'll multiply that by 9. Okay, so 0.433 times 9, right? The answer turns out to be, this is 3.897 squared centimeter. This is the area of an equilateral triangle. Alright, so I could say this is roughly, to the nearest whole number, it is roughly 4 squared centimeter. How? 3 is the nearest whole number, clearly. And after a 3, you have an 8. You could write the 8 up as 1. The 1 is added to the 3 to make 4. And I could drop every other digit. So this is roughly, okay, for the area of an equilateral triangle. Alright, so let's move on. We need to build this for a while, when I rub off in a moment. Alright, okay. So let me also say this. The area, I've talked about the perimeter, right? It's the distance around an object. The area is the space within or inside the object. So if I shade this, the shaded portion here, right, is simply the area of the object, the space within the object. So let's talk about a few more other types of triangles. So I'll talk about the isosceles triangle. That's the triangle, okay, whose 2 sides and, okay, adjacent angles are equal. So number 2 is isosceles triangle. So it's a triangle like so, okay, whose 2 sides, okay, and 2 angles are equal. So if this is angle A, this is also angle A, right? Okay, alright, and whatever the value of this side is the same as the value, okay, of this side also. And you are free to imagine, okay, let me just take in the angle A, call this angle B, angle C. So in other words, okay, this side, this line segment AB, the line segment AB, okay, is the same as the line segment AC, okay? And also, this angle B is the same as angle C. Okay, this makes this isosceles, right? Now, Okay, and you are free to call this side now A, and okay, I'll stick in a B here. So the perimeter is the space, just go around it. You sum up this value, okay, the value of the side AB, AC, and BC. Okay, that gives you the perimeter. Now, let me talk about the area, okay, which is really the space within. Now, this area is simply, okay, the side B squared over 4, okay, this is times the square root now of 4 times the side A squared, that's the side that is given, the product of the two sides, minus the other side, okay, which is B squared, and this is in squared units, okay. So let me give an example. Let's say side A is 3 centimeter, this is also 3 centimeter, and let's say this is about 4 centimeter, right? So the area of this isosceles triangle is side B is 4 centimeter, is raised to power 2 divided by 4 times the square root of 4 times the side A is 3 centimeter all raised to power 2 minus the side B is 4 centimeter all raised to power 2, and I'm taking the square roots. Alright, we've been this for a while I wipe off. Alright, so what you see now is that this will boil down to be, clean this up in a moment. So the area of the isosceles triangle, becomes 4 raised to power 2 is 16, but clearly, okay, I lose one of the 4, so I'm left with 4 centimeter there. 4 centimeter, okay. The square root of 4, and I have 4 in 3 raised to power 2 is 9, so I have 9. Half centimeter squared out of that. Centimeter raised to power 2 minus 4 raised to power 2 is 16. Then I have centimeter raised to power 2. Right. Okay. So what this turns out to be is I have a 4 centimeter here, and I have a long square root of 4 times 9 is 36. 36 squared centimeter minus 16 squared centimeter. So I'll take the difference now. So this turns out to be 4 centimeter times 36 minus 16. This is 2, this is a 0. This is 20 squared centimeter, right? So it turns out to be that this is 4 centimeter times the square root of 20, right? And the centimeter square is also carrying a square, so this time the square root also of the centimeter raised to power 2. So I lose the square here. So it turns out to be that this is 4 centimeter times the square root of 20, and I'm left with, okay, a centimeter also. So when centimeter multiplies out centimeter, you're left with centimeter raised to power 2, okay? So I'll leave you out with this, right? All right, so let's proceed further. Or you could just break 20 down as, let me rewrite this. So this is just the same as 4 centimeter times the square root of 4 times 5, that's 20. This is in 6 centimeter, right? So this turns out to be 4 times the square root of 4 times the square root of 5. And this is centimeter in 2 places, that's centimeter squared. The square root of 4 is 2, so I have 4 times 2, and I have times the square root of 5 in squared centimeter. So you can just think of this as 8 root 5, okay, squared centimeter. And whatever the value of root 5 is, you can stick it in there, okay, and you get your answer. Alright, so let's move on to the other type of triangle. Maybe this for a while I clear this up. Alright, okay. So the third type of triangle we'll talk about is the scaling triangle. That's a triangle whose none of its sides or angles, okay, is equal. So we have number 3, that's the scaling triangle. Scaling triangle. Scaling triangle. Scaling triangle. So this is a triangle like so, okay, whose the sides are different in values, okay? And the same goes with the angles. This angle is different from this, and okay, it's also different from this. This is scaling. So you're free to call this side A. Okay, you will call this angle A, angle B, angle C. You're free to call this side A, okay? You're free to call this side B, you're free to call this side C. Right, so how do we really figure out the area of a scaling triangle whose, okay, sides and angles none are equal? So what we simply do is this, we have to take half the perimeter of this triangle first, right? So we call half the perimeter, we call that the semi or half perimeter. Half perimeter of a triangle, right? Of a triangle. And we denote that by a symbol S, half a perimeter. And that is simply equal to the sum of the sides, side A plus side B plus side C, divided by 2. Right? Then to really get what the area of this scaling triangle would be now, it's the area becomes, okay, the square root of the semi-perimeter, that is S, okay, into brackets, what this value is of the semi-perimeter or half the perimeter minus the first side, okay, the semi-perimeter minus the second side B, and the semi-perimeter minus the third side C, okay? And when you take the square root out of this, okay, you get the area. And by the way, we call this formula, it is called Heron's formula, okay? Some textbooks use Hero, but it's actually Heron formula, okay? It's Heron's formula. All right, I need to stick in some values here. Okay, let's just number crunch a little. So let's say I have a 2 centimeter here for the side. Let's say this is 4 centimeter, and let's say this is 6 centimeter, right? So let's really talk about how we compute the area of this. Can I rub off? All right. All right. Okay, so first of all, I'm looking for the solution. I'm looking for the semi or half perimeter. That's the side A is 2 centimeter plus B is 4 centimeter, and the side C is 6 centimeter, and I'm dividing everything by 2. So this turns out to be, this is 6 plus 6, that is 12 centimeter over 2, and I have a 6 centimeter, okay, for the semi perimeter. And of course, I'll go ahead and compute the area now. So the area turns out to be the square root, okay, of the semi-perimeter, that is 6 into bracket 6 minus the side A is 2, okay, semi-perimeter is 6 minus the other side, which is a 4, and this is the semi-perimeter, 6 minus the other side, which is a 6, okay, and of course, this is in centimeter, right, times centimeter, centimeter times centimeter, centimeter, right? So what we simply do is this. This turns out to be the long square root, and the square root of 6 into 4. This is a 2, and this is 0. Okay, so we'll just ignore that, right? And once I stick in a 0 here, let's say, right, it turns out to be that everything here, okay, boils down to be 0. Okay, so this is really not, okay, a feasible calculation. All right, so let's go ahead. This is the same as just like the square root of 0, and okay, it leaves everything with, okay, a 0. All right, so let's go ahead and talk about some other, okay, types. Now let's assume, for my convenience, okay, let's assume that this is a given scaling triangle now, right? The sides are given, but I want to make reference to a particular angle. So let's say, for example, that this angle B, okay, I give this angle B, let's say this angle B, let's say this is about 60 degrees for my convenience. So what should be the area? One angle is included now, right? So the area turns out to be, this side times this, right? So the two sides, right? These two sides, I'll take them into account. Okay, these two sides, right? And I'll stick in a half there. So I'll take A times B, I'm not including this because this is where the angle is facing, A times B, then I'm taking the sine now, the sine of the given angle, which is sine 60 in this regard. I know what your A is. It is a half, A is a 2, B is a 4, B is a 4, B is a 4, and of course sine 60 is the same as, okay, let's see, that's sine 60 degree. If sine 30 degree is a half, okay, and cos 30 degree is root 3 over 2. So it turns out to be that this is really the same as this. So sine 60 is the same as root 3 over 2, and that turns out to be 0.8660. That's root 3 over 2. And of course, I lose the 2 here, so I'm left with 4 times 0.8660. So 4 times 0.8660, 4 times 0.8660. It turns out to be, this is 3.464. So the area is 3.464. This is in squared. Okay, and you can leave the answer to either the nearest whole number, okay, or to some number of decimal places. Alright, so let's talk more about a few others. Talk about the obtuse triangle. Can I rub this part off? So I'll talk about the obtuse triangle. Obtuse triangle. Talk about obtuse triangle. Obtuse triangle. Okay, I'll talk more about this trig ratios, okay, shortly. Alright. So we have obtuse triangle. Obtuse, number 4, obtuse triangle. It's just a triangle, okay, whose one of its angles, okay, one of its angles exceeds 90 degrees, okay. So you have something like so, okay. So we assume for our convenience, okay, I'm assuming for my own convenience, okay, that this angle, okay, exceeds 90. So that makes this obtuse. Then you have acute angles, okay? All the angles in the triangle less than 90. Alright, then lastly, we have the right angle triangle. Can I rub this off? So you have the right angle triangle. The right angle triangle. So this is 5. The right angle triangle. Right angled triangle. Right angle triangle. So it's just a triangle whose one of its angles is exactly 90 degrees. So you have something like so. This is a right angle triangle. So that angle between this vertical and horizontal line is exactly 90. While the two other angles are acute angles, right? So you are free to imagine this to the side H. This is okay, side B. And you're free to call this, okay, let's say side C for your convenience, okay? So the area, and by the way, I could find what this other side is, okay, using the Pythagoras theorem, first of all. So the Pythagoras theorem simply states that this is, okay, if I now take a reference angle, for example, let's say this is my reference angle, the side opposite this reference acute angle this is the opposite side. So this turns out to be the opposite side. And where angle 90 faces is called the hypotenuse side. That's the slanted side. And the side adjacent to angle 90, this is, okay, the adjacent side. So Pythagoras theorem, or the Pythagorean theorem is used for computing the sides of a right angle triangle, specifically just for a right angle triangle. Right? So if two sides are given, you will find the third side or the other side. So this simply states that the square on the hypotenuse side is equal to the sum of the squares of the other two sides. So it's equal to the sum of the squares of the other two sides. So if I had taken my acute angle now if it is angle theta, this has to be exactly 90 degrees minus this angle. So if I'm using this angle now, right, this turns out to be my opposite side, right? Hypotenuse, and it becomes the adjacent side. Because let's say, for example, if I had 40 degree here, this has to be 90 minus 40. So this should be angle 50. Okay? So any of these acute angle, it's okay. So hypotenuse side, let me just call this a C. Okay, let me just, okay, I don't know for now. So this is now, I'll just call this X. X squared is equal to opposite side, that's H squared. Adjacent side is B squared. So to know what my hypotenuse side is now, take the square root of both sides, right? And I'm taking the plus or minus, but I'm interested in the positive part of the square root. So I lose the square and the root, because the square root of anything means that term is raised to power a half. So if you have the square root of x, it means x is carrying power half. If you have the square root of x squared, it means x squared is carrying power a half. So just like we have here now, right? And law of unity says even if a term is carrying a power and it's further carrying another power, the powers will multiply. So 2 times a half, I lose the 2. So I'm left with x raised to power, which is the same as x. And this becomes the positive part now, which is h squared plus b squared. So you are free to imagine that this side, okay, is the square root of h squared plus b squared. Okay, just for a convenience, you may be this for a while. And the area of this triangle, you are free to imagine, okay, it's half the base. So this is the area. Is simply half the base, okay, times the height. So we leave this part out. So this is okay, really what the area is. Alright, now let me now go back to the basics, okay, and talk about a few things just to lay a complete foundation. Can I clean up this? Alright, okay, now you watch this now. You watch this. So I have a generic representation of a triangle, okay, something like so, right, something like so. I know this is angle A, angle B, angle C, right? What this simply implies is the sum of these three angles, this angle, and this angle, right? So the sum of angle A plus the sum of angle B plus the sum of the other angle is exactly 180 degrees. This is, okay? Then if I extend this angle C now, okay, you figure out that this is angle C, that there is an exterior angle formed here. So the sum of the interior angle, this inner angle, so the sum of the interior angle plus the exterior angle, now this angle outside, right, boils down to the 180 degree. Alright, I need to wrap it up here. I will continue with the next parts of this lecture in a subsequent bulletin. If you're new to the channel, you want to like, share, and subscribe for more content. Thank you.